Welcome to today's Hydro Seminar. Today's seminar will be held by Dr. Mohammed Ghidaoui. He is the Chinese Estates Professor of Engineering and Chair Professor in the Department of Civil and Environmental Engineering at the Hong Kong University of Science and Technology. He will talk to us today about his presentation on the time reversal of waves, theory, experiment, and application. So please welcome, join me in welcoming Professor Ghidaoui.
Sorry. Okay, thank you so much. Can you all hear me? All right, that's great. Step one, do you understand me? Good. I thought it's only in Hong Kong that people sit in the back. All right, so apparently it's I gave this lecture or something similar back home. I'm from Tunisia, and the people just sit next in front of you, and then they hug you afterwards. So, well, that's a different kind of culture. And anyway, let me acknowledge first the funders, of course. Those who give us the money is the Hong Kong Grand Council. This is a 5-year project. We are in the 4th year now. They were kind enough to give us about just over $5 million US. This is our team of researchers, and I will go through them a bit later. They are a mix of civil engineers, mechanical engineers, physics, math, electrical, and so on. Okay, and I hope maybe as we go through it will become clear as to why we needed all of these expertise. Now, really when I started, I know nothing about this. I didn't even know it existed. Well, I mean, I know the concept, but I didn't know that they use it. But of course now it became the title because it's what I stumbled on along the way. So the mention of time reversal often does not sit too well with our intuition. And let me give you a video, an example. This is why it doesn't sit well, because it's difficult to believe something like this. So a bit of a music. All right. So you would be happy if this could happen, you know, when you break your glass of wine or whatever you like to drink. So that does not sit very well, because you've never seen it happen. Your intuition says that couldn't happen. Let me make a comment and I'll come back to it. Actually, first of all, that's not what we are doing, okay? And this is obviously a video played back, but physics actually does not prevent this. Physics have no problem. All the laws of physics does not prevent this from happening. So I'll discuss a bit later as to why then it doesn't happen, since physics allow it. On the other hand, I'm going to convince you, I'm going to show you that for waves, I don't need to play the waves backwards. You can play them backwards. Waves are very robust. You could actually send them back to and do what they did in the past, to find their past. So the idea is this. Essentially, you release a sound. It emanates, in this case, radially. If you have open space, you could have all kind of inhomogeneities. And let's say you happen to measure pressure at a couple of locations. So you're just measuring the pressure signal. All you need to do is take whatever you measured, time reverse it, means last in, first out, and hopefully that'll become clear later as to why, and you put that. This becomes your source. And if you are patient enough, you will see your wave conversion back to the point, to its original source. In fact, the first experiment that was done was in France, where they had mics around. You walk into the room to test it, and you say, hello. They tested it, they measure it, they send you back, and literally you eat your own words. Hello comes back and focuses on you. So now I'll show you a video of this. Okay, this is actually an experiment that was done in Brazil, not by me. The stone dropped, waves are emanating. I hope this is clear enough. Can you see it? Okay, so now what they're measuring at a couple of places here. They're not measuring everywhere. They're measuring just at a couple of locations. They will wait for everything to quieten down, and they're going to send this wave back. And if all goes well, the wave will converge to the point where the stone actually came down. Everything comes back except the stone. Right? And the stone is like the glass. Why the stone does not come back, we'll try to discuss a bit later. Now, let me see where we are. We don't need to wait for a long time here. So I think they already, I didn't pay attention, I was talking, so maybe they already send it back. Okay, so the idea they send back the signal from which they measured. Now, and again, if we're paying, sorry, let me play this again, but I speed through it. Now I'm going to take you to, this is where they start to reverse it. You see the wave is being sent now from here. Okay, whatever they measure, they send it back. You can find this in the internet, by the way. Okay, so now let me get you closer to gain a bit of time. Okay, so now watch. It start to come back, start to converge. A bit of patience, because it's worth it. You see it? You see it converging back? Boom. So it's actually back to where the stone was. Okay, so it actually goes back to its source. Now the one thing you notice, even if you send a point source, the only thing it could converge back is to a wavelength over 2. That's what they call diffraction limit. You cannot converge it back. So if you want to localize things, therefore, better, you need short wavelength. And that's why you go to ultrasound, higher frequency, short wavelength. The other thing you should notice is you do get back your source, but you get all of these, what they call side lobes. And the reason for those side lobes is you did not measure enough energy. You only measured it a couple places, so you could not cancel everything. Okay, so if you want to cancel everything, you either have to measure every wavelength over 2 around, or you have to measure in a couple of places, but for a long time. The idea you measuring for a long time is that you expect every wave to eventually pass by you if you are waiting long enough. So if you're measuring here, you wait, the wave will bounce back, and eventually you will pass by your measuring point. And then you could get rid of those. So please remember this lambda over 2 limit, right, and that there are side lobes. And we will see that all throughout the experiments. This is some experiments actually done also in a channel in France, and therefore that's why they have the Eiffel Tower. So in this case, they generate a wave in the shape of an Eiffel Tower in a channel. They're going to measure in a couple places, and they will time reverse it, and you will get back the shape of the Eiffel Tower. And actually, they had lots of fun with it. They use a smiley face and so on. Okay, so hopefully you can see it. Right, and that's what the reconstruction is. Now, that's gravity waves. Electromagnetic waves are also time reversible. This is the Maxwell equation. Okay, so again, you're going to get the source here, and they're only going to measure those 4 places. So you get the source, you measure there, you wait, you time reverse, and these become your source. And if you wait, you see, again, the wave collapsing and finding the source. Now, why this is great? One of the things is when we're localizing defects, defects are themselves sources of waves. Okay, when you send a wave, it hits on a defect, it reflects. So that defect itself becomes a source. So if you're finding defects, this is a great tool. So now they are doing the time reversal, and again, you will see it refocusing back. Okay, so again, initially, it looks a bit of a mess, but you need the number. How much time do you need? The same time that you went forward. So if you went forward 2 seconds, you need 2 seconds to get back. Okay? So you get the main lobe, you get the side lobe. If you want to get rid of the side lobe, you need to measure every wavelength over 2 again, or measure in those places, but for a longer time. Okay. Now, I'm going to skip through these because this is acoustic wave. You can prove that acoustic wave is also time reversible. One of the early experiments, this was done in the Mediterranean Ocean, actually close to my home. They done it over a range from 10 kilometers into 30 kilometers. They have a source. They have an array here of sensors. They send this wave energy. They capture it. They send it back, and the energy refocuses. And this is I will show you a short clip, actually, of a lecture by the person, the main brain behind that experiment. So they're going to send here sound source. Can we increase the sound? Can you hear it? Yeah, unfortunately, if we can turn up the volume, maybe they can. The idea, what you're going to hear is you're going to send a blip, a short pulse. So you're going to send a short pulse. When you hear it here, you hear it elongated. There is a lots of echoes. The reason for that is the energy. Some of it goes straight, some of it bounces up and down. So the wave gets dispersed. So you see it elongated, and then what they do when they reverse it, when you get back again, you go from that long elongated echo to just a blip, to just a burst. Okay, let's try it again and see how.
It only comes out from the laptop.
Okay, sorry. Again, this is in the internet. So now that person used this. He used it for many applications. One of the applications he used it for was for kidney stone. When in the old days, when destroy kidney stone, they just send a wave with a lot of energy. It destroys the stone, but it damages the tissue around it. So what he tried to do is use time reversal to see if he could just focus all the energy on the stone. So what they do now is they send a test wave. They don't know exactly where the stone is. They send a test wave, and you're going to get, of course, two peaks, right? You're going to get two reflections from the stone and from the tissue around it. From the stone is going to be stronger. So what they do is then they iterate. They take what they received, and then they send it again. As you keep sending it again, the big one becomes even more dominant from the stone, and the little one becomes suppressed. Now, really, mathematically, what they found there is the Green's function for the stone. When you know the Green's function, you can send then the energy using that response function to the stone only, and you only destroy the stone and leave everything else untouched. So that's what he's done with it. This is some of the usage. By the way, he's also, lots of these big TV screens that they use, the touch screen is actually based on this concept as well. When you're touching the screen, when you move your finger, all of those are point sources. And they measure the stresses around the screen. And they keep sending it back, and it keeps localizing the source, and they just map them out. So if you write an M, then you will see it an M, because they just map out the sources and so on. So it became really a place for, also the ocean one. They use it now for wireless communication acoustically in the ocean. They use it also for imaging fishes and under the sea. So for us, we wanted to see if we can apply it to underground water infrastructure, fluid in pipes. So what we wanted to see, if we could prove it experimentally like they did, is we send a wave here, capture it at the end of a pipe, and then time reverse it, and see if we could reconstruct it up to a limit of lambda over 2, or about lambda, the order of lambda. That's what we set out to do. So this is some of the experiments we were doing. So we essentially send from this transducer, we send a wave, we capture it here, and then after we capture it, we time reverse it, we send it back, and we find the only place that it refocuses, I will show you, is at the original location of that wave. Now, I want to make a comment here. I think everybody here is civil engineering, right? Or maybe mechanical. You got to remember, many times when I give these lectures, people say, waves in water? What is the Mach number? I say the Mach number is basically 0. How can you have waves in water? Because a lot of our fluid mechanics tell us that it's only when Mach number is larger than 1. Please remember, that's only one of the conditions. I think because a lot of those books are written by mechanical engineering. It's when your Helmholtz number of the order of 1 or larger, or when the Mach number is larger than 1, or when the fluid number, the acoustic fluid number, is larger than 1. So in our case, for pipes, we're always in this regime. What does that mean? What is this number? It's the wavelength ratio of the length scale of your domain to the wavelength. So if I don't know if you could see my pen here, I have a pen. If I want to excite waves along the pen, I need a wave of the length of the pen, or shorter, and you start to have waves across it, right? If you want to excite waves radially, you need the wavelength to be shorter. It needs to be of the same order as the diameter. So you could see you need higher frequency. So when I'm exciting waves here, I will excite the longitudinal waves first, and then later, if I keep the frequency going higher, then I will excite the radial ones. Okay, so that's the regime. This one is for geophysical application. This is the case. It says if you go deep in the ocean, very deep, because of the pressure, you could have change in density simply because of the pressure. And that's what the third condition is. So really for civil engineering application, we should be telling students more about this, right, rather than about Mach number. We are not running many things that... So now we wanted to test, remember these time reversal in pipes? So the first thing we wanted to do, though, let's understand the channel. Let's understand the acoustics, the waves in this pipe. So we did some experiments, and what you see here is the experimental frequency versus the wave number, and this is the model. The model, what we had is a wave equation in the fluid and shell theory for the pipe, okay? And we're doing some comparison. What you see here is the dispersion plots. So one of the things you notice, you see here below this, there is two waves. One wave is the longitudinal wave along the fluid. That exists all the time. The other one is along the pipe. And then if we keep the frequency increasing, eventually, the frequency increasing means the waves become shorter and shorter. Eventually, we excite the radial modes. So this is the first radial mode. It starts here. And this is the second radial mode. So if you go, you start to get shorter and shorter, and you excite. So it depends which frequency. So when we want to only have a plane wave, we need to stay below that frequency. And that's pretty much all of the, when people talk about water hammer, when people talk about pumps and so on, they're always here. They're always in this area. Okay, so they're only sending longitudinal wave. They are not exciting radial waves. Okay, so for these, you need transducers that operate at 20 kilohertz, 30 kilohertz, and so on. And why we want to do that in this project is, again, we want short wavelengths so we can localize things better. We can have higher resolution. Another interesting thing we found is we first wanted to look at the classical plane wave, or this longitudinal wave. And something really interesting came out of it, at least to us. By the way, we also measured on the pipe wall. So we measure the acceleration in the pipe wall and the pressure in the fluid. And they are both in agreement. This is what you see here is frequency. Sorry. This is low frequency. And we up the frequency as we go here. Here you get the plane wave. Right? Notice as we start to increase the frequency or making the waves shorter and shorter, all of the pressure, all of the energy is next to the pipe wall. This is actually the analog to shallow water. This is shallow water. This is deep water. If you see surface waves, in shallow water, you get the whole water column oscillates back and forth. In deep water, you actually get you start to get elliptical shapes and then down to circular shapes. And if you go deep, you actually don't feel the wave at all. And that's actually what is going on in here. And in fact, we went and studied then particle paths. And the particle paths, when you have low frequency, like water hammer, you get the whole column to oscillate back and forth. If you go further, then you start to get the particles to oscillate more near the surface, or near, and in this case, the pipe, and they hardly move in the middle. So the lesson we learned there, frankly, we were not prepared for this, is if we send out, and the reason we discovered is we put the pressure sensors here. We were measuring, we got nothing from that wave. And we said, well, what is the pressure? And then when we moved it radially, suddenly all of the energy is hugging the pipe. So now, we then wanted to experiment first on the low frequency, so we went to the field, and we opened a pipe suddenly here. We went to a fire hydrant, we create a burst here, and measure at two locations. An artificial burst, okay, and we'll show you that. So that's the artificial burst. You get two waves, and we capture them here. This is the signal we're capturing in the field. Then we time reverse them, and we will see if they refocus there or not. Meaning, this was already a nice experiment for us, because if we can show that it happens, it means we can find bursts very quickly in the field if we are measuring. If the city is doing real-time measurements and you see a sudden drop, and I'll show you a case where we use this in Hong Kong. Nowadays, when they have a burst, they promise within about 12 hours they will be able to solve the problem. Okay, and most of the time the bursts are known because somebody else reported there is a problem with the water, or worse, they've seen water, on the road. Okay, so this is, let me see here. Oh. So did it? Okay, so it's now reversing, and it's only at this location. So we're sending now these two waves back, and they refocus. You get the minimum drop there, okay, at the source. The width of this is about 150 meters. Why? Because the wavelength is about 300 meters. Why? Because my guys can only open the valve so fast, right? Because this is mechanical, so the wavelength is long. So if we want to do this, we have to make the wave shorter. Now we wanted them to go to high frequency. So let me quickly... So we went here, and we selected one of these frequencies. I think it's somewhere here. And you should see now 3 waves in the fluid. The plane wave is the one that goes longitudinal, goes straight along the pipe. These are the waves that's going to zigzag along the pipe. They don't travel in a straight line. They travel up and down because you're exciting the radial waves. So they're going to lag behind, and you will see that. And so you'll see 3 modes, essentially. And first, we've done the numerical experiments. So so we send a burst, and they get separated into 3 modes. The first one is the straight one. That's the plane one. This is the first mode. That's the second mode. The first mode zigzags, hits the wall. The second mode zigzags even more. So it's not going in a straight line, so it lags. So what we did then numerically is we then, took this, time reversed it now. Okay, so now we send, therefore, the third mode first, then the second, and they catch up with each other only at the source. So what is happening here is that, I always give the example. Imagine you have 3 runners. Here are 3 modes, 3 runners. Me and 2 of you. We start together. That's the burst. We go running, you're first, you're second, I'm third. You time us, and then you send us back. Because I was last, you send me first, right? You time reverse. So you're going to send me first, and then you, and then you. If we redo our run, we will meet at the starting point. Okay, that's the essential kind of idea. You actually undo the wave dispersion in that way. So this is a cartoon that we've done to kind of illustrate that. So that's what these other modes are not going in a straight line. They're wasting a lot of their time. This is the slowest one. Okay? So now, when you reverse, you simply send the slowest first. You let it go on its way. And then when the right time, that time difference, you send the second, and then you send the fastest, and they will meet there and only there. If you let them run, the fastest will beat, and they get dispersed again. Okay? So it's only at their source where these things will meet. So now, of course, this was all nice, but can we show this in the experiments? Okay, for these high frequency, and that's what this shows you. We have a source, we have all kinds of pipes, different material. You get the wave to be dispersed, and now we take what we measured here and we reverse it. And again, the refocusing, all the waves will catch up with one another, and they refocus at the source. And only, so we actually measure at all the different locations, and only at the source where you get refocusing. So now that was in the lab. I think the distance was about 6 meters or 7 meters. We want to test it over a much longer distance, so we did this in this facility that we have outside the university, and I think it was 50 meters. So this is what we send. We send it from here. We get it here highly dispersed. We measure it. We send it back, and you get this. So you get the male lobe, the side lobes. Why the side lobe again? We're only measuring at one point inside the pipe. So we are not sending back all the energy. Like I showed you with all the others, you're going to get the main, and you're going to get side lobes. So now what's the math for this? Can we, since it seems, so what will be, does the math work out? So I have this slide. So let's say you're sending a delta function, okay? You send a delta function into your pipe, and you measure. What are you really measuring? You can call it the response, or if you're a mathematician, you'll call it the Green's function. That's the Green's function of your pipe, right? So that's what you're measuring. Then you're going to take this, what you measured, time reverse it. So what are you going to do mathematically? You're simply going to make t minus t, okay? So you just take what you measured, shifted it, and now this is going to be your source. This will be your source. You're going to send it in, but you're going to send it now into a channel which you know already the Green's function for, right? You just measured it. So this becomes your source. You convolve that, so mathematically you're doing a convolution. So you're convolving your source with your Green's function. You could write it in integral form, and I hope you could notice that the only place you're going to get a peak is when t is equal to 0, right? If you have the inner product of two functions, they are maximum when the two functions are parallel, right? They are the same. When are they the same? Is when t is equal to 0. What is t equal to 0? Is the source. Your source started. So that's why they call it spatial focusing and temporal focusing. So it gives you the right location and the right time as well, okay, for the focusing. So now, therefore, it turns, all our exercise into finding these peaks. Okay, and that's what the peaks you're seeing experimentally, right? But of course, with side lobes, because we don't measure enough. So now let me make a comment back. Remember, again, our glass that was broken, and I said, actually, to physics, the laws of physics are time reversible. Newton's law, change t to minus t, nothing changes. Your energy equation, nothing changes. These are, we saw the electromagnetic equation. This is the Schrödinger equation for quantum theory. All of them are time reversible. So why is it then we don't get younger? Why is it that the glass of wine does not go back? So these two guys did actually quite a bit of work. What they did is they compared waves with particles. So they put a bundle here, I think 2,000 of randomly placed bundles. They send the source of the wave, they measure it here. So the wave has to go through all of these bundles. So it's going to get multi-scattering, right? And then they measure and you get all of this mess. But when you send it back, you still get a good reconstruction. Okay, so the wave does reverse, even in this very highly inhomogeneous material. Then they want to compare. They did this with particles. You release a source here, you capture them, and here you reverse the velocity. These are scatterers, like these. You send them back, and you get a couple of them that collect in the original place, but they are everywhere. Okay, so you couldn't get it like the wave. You couldn't get the refocusing. So what is the reason? The reason is that when you measure, you're always making an error, right? Measurement errors. So when you're doing the time reversal of waves, you're making an error, but the errors only grow as its square root of time, meaning you are not actually going to lose it very quickly. So the errors do not grow very fast. And that's why waves are robust to time reversal. But for particle, it's chaos, nonlinear dynamic. They grow exponentially in time. So they separate. Physically, the intuition is this. With a wave, it has a finite length. So the wave is almost going to hit everything it hit before, okay, because it's large enough. But for a particle, you've displaced a little bit, and it will miss totally its path. Okay? It cannot undo its past path. So therefore, it turns out, because this was a big debate, actually more than a century ago, between Boltzmann and Locksmith. Boltzmann said entropy, because this has to do with entropy. Boltzmann says entropy is really a probabilistic concept. Essentially what Boltzmann said, the glass of wine, or whatever glass, can actually go back, but the probability is very small. Right? Says it can happen, but don't really gamble on it. Its probability is very small. Locksmith say why? There is no reason. If I measure, physics tells me. So the explanation now is that if you can measure accurately enough, yes, you can, but we never do. So now, how do we build in these concepts of entropy? In all our models, I'm sure in your mind you're saying there is damping, there is damping. So what do we do with damping, right? So when we have spring-like, we build damping, and you know that breaks time reversibility. And that's why to people, when we show this, they say, but damping, what happens with damping? So let me tell you what happens. This is the equation we are solving. These are the ones I compared experimentally. So you have the wave equation in the fluid, and this is the shell theory. Every one of these is actually time reversal. The only one that is not is the material. When we are using a viscoelastic material, the material property, we get here this complex conjugate. Time reversal in the frequency space becomes conjugation. So the only way that this is exactly the same is if this is a real number. When this is a real, the conjugate of a complex number is itself. But when is it really, this is truly real, is when you have elastic material. Viscoelastic will always have. So we wanted to look, because we did it in the pipe, and it seems to reverse. We did it in viscoelastic. So we studied this part of the viscoelasticity, and we find this is the imaginary part. This is the one that will try to destroy that time symmetry. The damping is only large for a certain range of frequencies. But beyond those frequencies, actually, there is no damping. Here's what's happening. The viscosity of the pipe has a certain time scale. The wave has a time scale. When the two match, you get the highest damping into the pipe. When the wave time scale is much, much faster than the viscous time scale of the pipe, it does not feel it at all. The wave does its job and finish before the pipe wakes up, before the viscosity knows that something has happened. Now, but that still does not answer, because many times we're measuring here. So you say, what do we do when we measure here? Okay, how do we still can use this concept of time reversal? Well, what we worked on is, can you compensate? If you know the model, can you compensate for the loss? So I'll give you an example. What do we mean by compensation? Say you have a spring solution, a damped one. This is a damped spring solution. This is the undamped. We can show mathematically you could map one into one by shifting. Okay? If you shift the time, you change the amplitude, you could actually map the damped into an undamped signal. Okay? You could restore it back, and what it means is this. So actually this is, we solved for the damped spring, you get this orange. We undamp it through that transformation, and you get back the undamped solution. So you say, well, that's wonderful. Then there is a catch, because this is what mathematicians call this an ill-posed problem. Why? Because you're adding energy. If you had no measurement error, there is nothing wrong with it. But if you start to make measurement errors, you're also adding energy to the measurement errors. And things can blow up. And this is what we've done here numerically, is we added a bit of error, and you see these errors grow, and eventually you don't get it. Initially you get it. But for imaging, we're always interested in a short. We're always interested when the wave goes and come back. We don't need to wait many wave cycles. So it actually works quite well for us when we are in that regime. We can compensate for that energy. So we did this. We did the same we mapped, this is the response of a viscoelastic pipe. This is the response of an elastic pipe. Then we did this mathematical mapping, and we show that analytically we could map this into that, and that's what I'll show you here. And we have a paper published on that. Okay, so this is what you discover. From this you get back your signal. But again, when we add errors to it, which we do, when you measure you're going to have errors, it will start to blow up. So we need to do some regularization. okay, like with all of these ill-posed problems. But we applied it experimentally with regularization. So this is the undamped signal. This is the damped signal. And we want to just see how this is experimental results. So we took this and we applied this transformation to it. And it's actually really promising. You get all of these peaks of these modes, but of course you get these things, right? These things are those small errors. They are also growing. So that's kind of the balance. We have to be careful. But again, luckily for imaging, we don't need to wait a long time. And also, the most ones that carry the energy are these peaks. So if we could restore those, we are in pretty good condition. So now, our application, really, I did it this reverse. We started by this project, okay? And this is our team members from mechanical, again, electrical, in different places. So I'll save a bit of time and skip through that. This is our advisory board. One of them is here. Okay, our advisors, again, from different departments, different places. Now, what is the problem we try to solve? We try to solve this problem related to water supply. I don't think I need to convince you about how important water supply is, but what you may not know is or some of you may not know, is worldwide we have 30% of the water leaks out. There is all kinds of defects. There is all kinds of blockages. This is pipes. This is a pipe that was dug from the ground. That's what it looks like, okay, after 10, 15, 20 years. It depends where it is. This is malfunctioning devices and so on. The amount of water we lose is enough to supply about 150 cities like Hong Kong. Okay, that's the amount of water that is being lost. The other thing that tends to be forgotten is that every time you lose water, you lose lots of resources, energy, all the material that went to treat the water, and so on. Okay? When you add that, the World Bank estimates the direct value of this money is about $40 billion US per year worldwide. Okay? That's the direct, not the indirect cost. So it's a real problem to try to address it. So when we set out was, can we find a different way from the way they are doing it today? So hopefully we can move forward. And we thought of waves. So we wanted to study waves deeper and see if we could find a way to use them to diagnose these pipe systems. Why waves? We all know from all these applications, medical application, etc. They are, if you have a system which is not accessible, complex, and so on, one of the fastest, the least intrusive way is to send a wave, you get the echoes, and you could do these imaging in a fraction of at least in a couple of seconds. And that's what we wanted to kind of work towards a system that does that. Now, we are not fancy, so our case, we don't really have a lot of accessibility to these pipes. So the only point to access is a fire hydrant. So we send the waves through fire hydrant. That's how we're going to probe them. And that already makes things very difficult. I keep saying to people, that's like saying it doesn't matter what your ills are. You go to a doctor and say, oh, I'm going to image you. You say, I only allow you to image me from my head. You know, and meanwhile, your ills are here. That's quite a challenge, okay, to do. But that's what we have now. This is one of the things we face. We're trying to convince the city for new pipes. Hopefully, we can do better. So smart things about cities make our infrastructure more accessible. Okay, it's not about being gadgets. It's about really allowing your infrastructure to accept future technology when it comes in, and you can adapt it. The other thing that now I showed time reversal was all beautiful, but in reality you have noise, right? You have traffic noise, you have all kinds. What we did first is we showed that time reversal still remains optimal. Optimal in a sense that it gives you the best search method in terms of maximizing signal-to-noise ratio. If your noise is normally distributed. That means if it's Gaussian distributed. So, of course, is it then Gaussian? So we went and measured in New Zealand, we measured in Hong Kong, we measured in Italy, and we measured inside the pipe, outside, to sort of compare. So we measured in the fluid and also by the road level. And inside the pipe, it is pretty much Gaussian in most of the cases. It actually fits this alpha distribution, which I never heard of before until we start doing this. This alpha alpha is a parameter. When alpha becomes 2, you get the Gaussian. When alpha is less than 2, it starts to diverge away from being Gaussian. And one of the problems with alpha being less than 2 is actually it does not have a standard deviation. This is a crazy distribution that it has a mean but no standard deviation. It's infinite because it becomes heavy-tailed. But luckily, we don't have that in the fluid. We have that outside. Outside, when you're measuring in the road level, it tends to be more this alpha-type distribution. So now we did this in 2 modes, active mode and passive. So we had lots of measurement in the lab, but I'll show you some field testing first that we've done. So these are some of the tests that we've done in Hong Kong. I think it's here. Also in Hong Kong there. This is in Milan, Italy, and this is in Trento, Italy. So I don't know where Marcelo and these guys take you to do field measurement, but we take you to Italy. So if you want to go to a nice place, and Milan at that, you should move and work with us instead. All right? You'll see now the tough life, my students. So this is a video of where we're doing actually one of the field testing that we're doing. We kind of took a video, and you'll see beautiful views. Okay, so this is where the students are working. We're doing measurement for a pipeline that is under the ground, obviously. Here there is a school. In fact, I received a phone call of a very upset headmaster. He says, "Why are you guys wasting my water around the school, and it's dangerous?" So I had to talk to him and convince him that we are really doing some research that is worthy. So now we became friends. He thinks we're helping the Hong Kong life. Okay, so this is the pipeline we were testing on. All right, so these are the views we get from our field testing. Not bad at all. Now, just show you the protocol of what needs to be done. So this is our source. Okay, we're going to be sending the wave from here. And the experimental setup maybe without my glasses now. We have to do some disinfection, of course. Okay, setting up the computers to collect the signals. The signal we need is about a few seconds, 3-4 seconds. That's all you need, because these waves travel at about 12 meters per second. That's a kilometer, more than a kilometer per second. So we send now the wave from here, and you see that the idea is we choose our guys who are really good to close these valves as quickly as possible. The reason is you want the wave to be short, because you want to have better localization. Remember, the localization is lambda over 2. Lambda is actually your wave speed times your timing. Okay? So now we have actually all of these automated, so I'll show, we don't need, when we did this, we had to take the signal back to the office, but now it's all automated. We get the signal and it automatically predicts for you what is going on. So let me skip through this and show you some of the results we get from it. So this is the signal we collect. We put it through time reversal, and we get all these multiple peaks. These peaks now should be mapped into singularities or things in the system. And we went one by one. So one was the fire hydrant itself. One of the peaks was associated with that. One was here. When we find it, we looked at our maps. There was nothing there that identifies. So it's either there is a leak or a blockage or something really crazy. So we asked them, we said, "Do you have a pipe here that you've forgotten to tell us about?" No, we didn't. Right? But after a couple of days, they came back and said, "We found old maps, and yes, there is a pipe that actually goes from there to there." So the pipe is still at its original location. So these things are a tool. It's not really for finding leaks. It's actually for mapping some of these underground. And you got to remember that most cities don't know where their pipes are. In fact, in our university, it's only 25 years or 28. They told me they went to look for a leak. They could not find the pipe. Okay, so they dug. They didn't find the leak. They didn't find the pipes. So the pipe was not there. It was somewhere else. So these things, and the university is not very old. And now the other one, when we did this, we said, let's try to emulate what the doctors do. Let's measure every 6 months, do regular checkups in the system, because you could tell easier on a change. And we did. For the first 2 times when we measured, we didn't see anything here. And the last time we measured, this last spring, we see something reflecting dynamic. And we said, did you install a new pressure release valve? They say, no. So again, they checked and eventually came back and say, yeah, our engineer put pressure reducing valve. So, and why did we guess it was a pressure reducing valve? Because what we did with, sorry, oh gosh, I didn't. What we do is also have a spectrogram. I don't have it here. We also plot a spectrogram. So in the spectrogram, you could see the frequency over which these different discontinuity act. And it looked to be in the frequency range of a pressure-reducing valve. So we could tell the difference between a pump and a pressure-reducing valve, etc. Now, we did this in Yulong, so they trusted us because we found things that they didn't know that in their system. So now they invited us to test in another area. And we reckon we found a couple of leaks for them. Okay, in these 2 locations. They already fixed one, but this one said you have to be certain. Our reputation is on the line, because that's one of the major highways between Hong Kong and mainland China that brings all our food, etc. So they said, if you want us, if you are sure, because we have to call the police, they have to divert the traffic, we have to dig the road, and the last thing we want is we don't find anything in there. All right, so now we are going there and trying to do more measurement to ascertain. But at least with the other one, we did find it. Then we tested this also in Trento, Italy, where, again, we find 2 peaks in here, and the 2 peaks were traced to, one was in fact a leak, which they fixed, and one, we found an air blockage. The system was rising, and there is air that was actually blocking a part of the pipe. So they had to put some pressure release there to get rid of the air, to degas it. We also tested in Milan. In Milan, the way we generated the wave was to trip the pump, just turn off the electricity to the pump. And what seems to the signals tell us that about 5 kilometers away, we're getting some really crazy peaks here. And in fact, they found, I think, about, in that area, they found a bunch of about 8 leaks, okay, bunched up in those areas. Okay, so these are, we're doing now as we speak more and more tests. Okay, now this is another interesting one. Again, I come back, many cities, including ours, are going into smart city. And I think the idea was they bought all these sensors, they put the sensors, and it's beamed to their laptop on their iPhone. And these engineers, they were watching live what is happening in their water distribution system in a section of Hong Kong. They were measuring at about 250 hertz. What they learned from it, though, is how dynamic the system is. This system is very, very dynamic. It's living. It's always, we teach undergraduate students a hydraulic grade line, and we make them believe that nothing moves, but in reality, it's actually crazy. It has a life of its own. But what they notice is that each day, around 4 o'clock, there is a drop of pressure, stays for a few seconds, goes back up. And they said, what's going on? The contractor who sold them this tried to look. Eventually, they ended up walking around on foot to see if they can find the problem. Well, so when we heard of it, we said, why don't you send us these signals? So we did get them, and essentially we time reversed them in the computer, and we were looking for where they peak. Okay, so they peak there, said, why don't you try there? Just go around 4 o'clock and see. You may find something there. It was already promising when we sent them this, because they said, oh, we have a fire hydrant here. So maybe somebody is really stealing water. But why stealing water every day at 4 o'clock? This is what happened. It's another government department that comes in every day around 4, fills the tanker, open the fire hydrant, fills the tanker, and go. Okay? So now at least they know that somebody was taking their water. So you do. So the lesson, I guess, and this is what I'm working with them now, is yes, you can get data with sensors, but you need knowledge to support it. Otherwise, it becomes a frustration. Right? You get all of these things. They were frustrated. They said, this is useless to me. I'd rather not see the drop than see it and not know what's going on. So this is what we've done more than 400 tests in Italy and New Zealand and Hong Kong. And this is a success rate in terms of finding things versus what we used to do. I mean, some of it is actually, by the way, this is pretty much everybody in the group has been working in this field from Italy, from New Zealand. So we are beating ourselves. So nobody is upset, right? So, but we are beating what we used to do by quite a lot. Now, when we set out to do this project, we wanted to do the low frequency, what I showed you, the valves and pumps and so on. But we knew that that's not going to give them very good resolution. So we are pushing now, the idea is we can use low frequency to sample over 5 kilometers or so, like in Milan. But what we could not tell in Milan is where exactly those leaks are. We told them a radius of 400 meters, right? They said, well, that's better than nothing. We said, can we use high frequency, 20, 30 kilohertz, and we'll be able to zoom in. So these are, so far we can only test them in the lab because nobody is allowing us to put sensors yet inside the pumps, inside the pipes, sorry. Okay? And there is no access point to go in. So here is some tests where we did, I forgot here, 20 kilohertz or whatever, where we can now localize a leak, and it can also identify the support. You get reflection from the support. So you could identify the two of them. All right? So that kind of shows you the resolution that you can get from these. You could also find the junction of this, because there is a difference in material, so you're going to get change in impedance, essentially. You get some reflection, and you can locate it. Now, the lobe here, the width of this lobe is no longer tens or hundreds of meters, is now a few meters, because the frequency is very high. We became confident. We said, why not try to put this and see if we could find something like that in the pipe? Can we send the wave and see if we can localize it? And it does. We can localize things that small. So this is telling us that maybe when pipes start to lose, their lining, we could really have a hope of seeing things happening before they become a major problem. In fact, to test that further, we took a real lining from a real pipe in Hong Kong. It's bitumen. In the old pipes, they used to put bitumen as a lining, and some of those are still in use, and it starts to come off. So that's what you see here. And we test it, and you get very good reflection from it. We tried this with different frequency to show that as you make the frequency, better resolution. The width of this becomes smaller, and in fact, the proper length scale is in fact the wavelength, because we can collapse all of the curves into one. Okay, so when you non-dimensionalize everything by the wavelength, all of the curves collapse. So we became playing with this, just test anything, because I talked to my structure colleagues. I said, how is the field of health monitoring of structure? They said, not, at least what they were working on, they didn't seem to think, they seemed to think they ran into a kind of a dead end. I said, why? They said, because of non-uniformity. I guess you get all kinds of rebars and so on. Well, that, to me, because everything I read about time reversal is that it actually likes non-uniformity, because every non-uniformity sends reflections back. So you're and every of those reflections, let's say you have a crack. So let's say there's a crack over there. When I send a wave, and if there is only the crack, I get one reflection. But let's say there is a non-uniformity behind it. I will get the hit from there. The wave will also go to you and then hit the crack again. So I'm getting double now, more information from it. So that's why they like it. So we try to actually illustrate that here. So first, there is no non-uniformity. So we did this, send, receive, and again, just playing. The student actually sent me this about 10 days ago. So this is the signal that we collect, and this is the time reversed. You get the male lobe, but plus quite a bit of side lobes, because we're only measuring at one location for all of that space. Now we went in between and put non-uniformities to see what it does to that lobe. And you'll see that lobe actually becomes thinner, meaning you get in better resolution actually with non-uniformity. So this, the width of that, compared to this. You get much better sharp corners there. We tried this also with different material. Again, this acrylic. And now we're showing what happens when you get the frequency higher. As you get the frequency higher, again, the same phenomena happen. So we're really just starting to play with this. So I'm talking to my structure colleagues. Maybe you could look at the idea of putting a project together. Okay, so that's all I want to say. Really, we started out by trying to solve or make a big dent in this defect detection in pipes. We ended up actually having much more fun with these time reversal of waves and the physics of it and so on. I must say that I probably learned much more about that than about the real problem. But that's what we could do in academia. I need to mention here that it actually has a lot of potential in civil engineering and in many, actually, in climate. Recently, I'm reading a paper where they say one of the things we have not been doing well for climate change is we have not been listening to the climate. We've been measuring things. We have not been measuring the acoustics. Yet, you got to remember, acoustics actually store a lot about material property. Because when you have a wave, you shake something. That's what waves are. When you shake, it tries to go back to equilibrium. What brings it back to equilibrium is the properties. So you're actually getting information about how fast it goes back and so on. So they use it in the ocean to find the temperature, okay? That they call ocean tomography, because the wave speed depends on temperature. They measure the wave speed and they map it back to temperature, right? Recently, they measure sound waves. They detected sound coming from ice cracking because of the ice melting. It actually travels in these channels. Please remember that in the ocean, at low frequency, at about 20 hertz, you could send the sound about 6,000 kilometers. So whales have been known to communicate for over 6,000 with no